So, Pierre, are you ready?
Yes.
Okay, so Pierre will start by talking about groups recognizing coordinates.
So, thanks a lot for the opportunity to speak. I'm very happy to start the first seminar. And yeah, I'm also very happy to be here. I think I really love my office, and I'm really looking forward for this month. Yeah, very fun. So, title of the talk, I'll write it down, on groups recognizing coordinates. And it's a joint work with Gannon and Ilijas. So, if I'm over 1 hour, just let me know. I don't want to be over time. I was discussing once with Martin else about what's the number of notes you need to have for 1 hour talk. And he said 4 pages is good, but I'm not sure it was meant one-sided for him. But for me, it's one-sided. I'm usually slow, and I think I will be slow.
It's also very hard to match Martin's speed.
It also depends on how stupid your audience is.
No, I don't think so. I close it because I want access to this board. And I start with an example. So starting example. Which is this group. G is the omega product of S3. S3 is a symmetric group. And the concrete question, what do we define in this group? So what is defined? And usually to answer this question, or the first answer to this question is describe a language of quantifier elimination. What can we define in this group? And also an answer you get often when you talk about products of a single structure or structure is you should look at Feferman-Vaught. So I'm going to recall what is the term of Feferman-Vaught, and it's indeed useful here, but it's only half of a story. And for the first, I would say the first half of a story, what can you define in this group? Well, you need more materials, and it's my goal here to introduce it. Okay. And the first thing I do is to be a bit more general, and not only talking about product of structure, but also reduce product of structure. So, and I'm going to explain afterward. But reduced product. I don't know if you are familiar with this notion, but I have to introduce it. And for that, take a family. And I in double bar I, mat BBI, family of structure, of I structure. And let I an ideal of double I. What does it mean? It means I is a subset of P of I, and you prefer probably to think about it as the complement is a filter. So J in I, if the complement J in I is a filter.
So actually, already now I can't distinguish between your two I's.
Yes, so there's only two I's, but double bar. Up, double bar. Double bar is my set of indices, and just one bar, but also curly, is my set of my ideal. Thanks. So, and I will denote the reduced product of Mi this way, and it's referred to the product represented by an equivalence relation, namely the following. AI is equivalent, according to I, to BI, if for all but I mini i's AI is equal to BI. Or if I write down what it means that the set of i's of indices such that AI is not equal to BI is AI. Okay, so I just describe what you can neglect, well, what is negligible, or what is small. When you consider the filter, and this is a set, and you can also equip it with an L structure. So L structure on the reduce product of MI is exactly what you do for ultra product or structure, namely that you write R, where R is a relation of AI, if only if for all I but I mini MI satisfy R of AI. So here it means for all but I mini. So particular notation that I'm going to use later. And for the function, it's even simpler. You set f of AI. The class of AI is the class of f of AI. So technically, it's also a class here. Okay, so that's the definition of reduced products. And what do you mean? What do I mean by set of supports? It's clear what is the coordinate and what is a coordinate in a traditional product, but what does it mean a coordinate in a reduced product? For that, you need to consider a quotient of the Boolean algebra. So the set of supports of the reduced products is what I denote PI, and just the quotient of the subset of I, quotient by the relation I, meaning A is equal to B if only if the symmetric difference of A is negligible. Alright, and this is my set of indices for this reduced product. It's a Boolean algebra, the same way, that PI is. And so just for an example, the standard product, PI, is also a reduced product. Here it's just an atomic Boolean algebra. If you consider the set of indices modulo I, where I is phi, I'm going to define what is phi. Phi is the ideal of finite sets. Then it's atomless Boolean algebra. Phi is the ideal of finite sets. So, two elements in the product are the same if they are the same but for finitely many coordinates. And it's a different property, it's atomic, it's atomless, and in general what do we get? We get any kind of Boolean algebra, at least modulo theory. So what I mean is, if you take a set of theories of part of I modulo I, so sorry, we have a short notation for it here. P of I, where I is an ideal. Well, it just is the set is all the theory of Boolean algebra. So when you run over all possible ideals, you get all the Boolean algebra modulo up to equivalence. Not every Boolean algebra is of this form. I don't think so.
You mean all completions of theory of Boolean?
Okay. Well, I have a Boolean algebra. I have a set of supports. I want to define the support with support functions. So support functions. And because I want a bit more general, to be a bit more general here and not talking about support of groups, but support of any structure, any product of structure, I don't have a constants, like I have E in groups. Okay, so how to define the support? The best way you have, the best analogy you have is this function that I am going to note support of equality between two elements A and B, which is simply the set of indices such that AI equals BI, and this is of course modulo I. More generally, you can define some other functions. I'm going to do now. So, what is this function? It's a function from my product square to PI. If phi is the formula, then I define the phi of a tuple A to be equal to the set of indices in I, such that Ni satisfy phi of S. And this is the class modulo. So I hope it's clear. Just mean it's the set of indices where formula phi is true. Slightly the same thing, but if phi is a sentence, I want to change the notation slightly. If theta is a sentence, then it's not a function from my product to the arity of A, just so to a 0. So sup theta, I'm also going to denote it by constant theta. And it's a set of indices in I, such that Ni satisfy theta. Okay, so here it's not a function anymore, it's just a constant in PI. Okay, so I just want to risk an analogy with valued fields to explain why I'm considering reduced products and not just product, what we are interested. If you just consider products, you end up to only considering this Boolean algebra, the atomic Boolean algebra. The same way that if you only consider valued fields valued in Z, you are going to talk too much about Z, about property of Z. Here, and the principle of Axe-Cauchy-Nash, for example, will be less visible. Okay, if you only talk about Z valued field. Here, by just considering all reduced products, you are also going to have an Axe-Cauchy-Nash principle, and you are not going to talk about property of atomic Boolean algebra that we already know, but you are going to talk about really the transfer principle. So it will be more accurate. Okay, so it's a bit of a risky analogy, but one more thing, what we know about Boolean algebra, pretty much everything. Okay. So the theory has been characterized by these invariants, 3 invariants which determine exactly the theory of Boolean algebra. We don't talk much about it, I think just because there is nothing else to describe there. And with what that said, now I can finally introduce Feferman-Vaught. So, while I'm raising, I'm explaining. So, it will not be the usual way to describe Feferman-Vaught. The formulation I have here, I first saw it.
Yeah, you better make it wet.
No, it's already
Yeah,
wet.
it's wet, okay.
But I'm just surprised of the side of. Okay. And which I don't like because I use both to clean, to record. Okay. I don't like that.
There's like a 2 in 1 here. I've never seen that before.
Because what I do with the water.
Some people do this. Separate things.
Okay. So the formulation that I'm going to present, I saw the first time in a talk of Hausdorff. I never saw it written somewhere. But it probably exists. So, theorem, Feferman-Vaught, and it's Feferman-Vaught for reduced products. So I don't know if it's really due to Feferman-Vaught or people work with it. But you can find this version, Feferman-Vaught for reduced products in Kessler is Shang. So, the structure. So you have a product of Mi equipped with a language N, one sort. Second sort is you have Pi with the language of Boolean algebra. And finally, you have the subfunction, sub phi, where phi is the formula. But I need to add also the sentence. The sentence are here in this sort. Well, eliminate quantifiers. Quantifier in relative to the Boolean algebra. So, okay, Feferman-Vaught insists also a lot about algorithmicity, that you can find an algorithm which tells you how to do that. Here we don't need it, I just need the quantifier elimination results. What does it mean, relative quantifier elimination? It just means if you understand definable sets in the Boolean algebra, which we do, then you understand all the definable sets in this structure. No surprise for now. So, just a product and a structure, and now you can talk about the set of indices where certain formula is true. What else I wanted to say about it? Let's call this language the language of Feferman-Vaught. And the natural question which arises is LFB interpretable in N? The best question is when it is. This is not always possible. Okay. If Mi are just infinite sets, product of infinite sets is an infinite set. You're not going to define a Boolean algebra in it. But the question is here, if you only have a structure here, can you find L formula which interprets Pi and sub phi?
I'm missing something, I guess. So if the product has one factor, what is this?
That's a very good question. It says that if you modularize, you have quantifier elimination.
By adding the support of phi, because it will tell you for which elements in your structure phi holds.
Do you believe me? If you have just one component, one coordinate, adding all the sub phi, just tell you for which element A the formula is true. Just say you have modularized it. So that's why it's working without other assumptions. It's because it's a lot to add this function sub5. It's a lot. But it's also why Feferman-Vaught is only half of the story about what is definable in the product of S3. Because we haven't answered this question. Is L Feferman-Vaught interpretable in L? And well, if you look at the work of, I think, Pagentire direction about Adams, they are exactly doing such a thing. Okay, but just for product of rings. Here we are doing it generally. Some other stuff, but this is more general. All right. And to answer this question, I need to define, and I'm going to use this part here of the board. What is an H formula? I mean, you notice the similarity between reduced product and ultra product. It's defined the same way, just ultra product is an ultra filter. And here you do the same thing with a filter. What is important in ultra product is Wash theorem. So what is the analog of Wash theorem in reduced products? It's not true for every formula. Every formula will not transfer like it does for ultra product, but it's true for a part of formula called H formula. So, to define it, definition, H formula. And what is H is, I don't know. I don't know what it is. Maybe it's own, but it's also very confusing. There's something called own formula, which is not the same thing. It's not included, there is no relation. With the definition though, or one of the definitions is similar to own formula. So it's a bit confusing. H formula is the set of formula, is the smallest set of formula. Such that containing atomic formula. So all atomic formula are H formula, enclosed under a certain operation. If psi H formula, then there exists a x, such that phi of x, and for all x, phi of x imply psi of x. And I probably make a mistake to write down the variable, because you apply this principle most of the time when it's a dummy variable. So, okay. Atomic formula enclosed under this construct. If x is a dummy variable, you get phi and phi implied psi, so you get the conjunction. Okay. So in particular, closed under they exist for all conjunctions. Not closed under negation and disjunction. So it's a bunch of formula. This description, it was my papers. This description is not enough. You really need this thing. Okay. Okay. And as I said, we have a Wash theorem for H formulas. Are you okay with the definition? Sorry.
We're laughing at you, but
I get used to it, but when I have two tools in hand, not only one. It's quite big. There's not many papers about H formula, at least that I am aware of. We work with 2 papers, I guess, concerning H formula. So it's not very well known, but it's much more practical than Horn formula. Horn formula, the definition is horrible. It's not compact. And also, this seems to be the correct notion. Well, because of this terrain proposition, and it's by Gannon. Let's say that let's how do I phrase it? Let phi is an H formula. So it works for every reduced product, no matter the L structure, no matter the idea of calling an equivalent. One, the product of mi satisfy phi of A, and 2, for almost all I, mi satisfy phi of A. So exactly like wash. Sorry, it's not a surprise. I was supposed to write it down, but it's exactly like wash terrain, except it's only for H formulas. Okay. You have a reciprocal to this fact, but I need to be careful when I state it. And it's due to Omarov. So position Omarov. If fix and I is a family of structure of L structure, if for all ideal I, the product of I satisfies phi of A if only if the structure mi satisfy for almost all I, for all I but only mi satisfy psi ai, then phi is equivalent to psi, equivalent to an H formula. In the commentary of all MIs.
Sorry, do you mean phi and phi?
Phi and psi. So here I have a phi, here I have a psi, and here phi equivalent to psi. I think I should have not bothered with phi and psi. You can say psi equal phi.
You're saying that the formula phi equivalent to psi is equivalent to an H formula?
No. Both are equivalent to the same H formula. Okay. I'm not going to bother you with psi. Sorry. It's okay. It's fine.
And you mean the phi is equivalent to an H formula inside the theory of
all MIs. The commentary of all MIs.
So this is a double bar phi.
Yeah, good point. Very good point, because it's for all ideals.
So this is the theory of the family or
The commentary of intersection.
of the intersection? The intersection of all the theories.
Yes.
Okay.
So the point is equivalence quantifier about all families. So you could say H formulas are characterized as exact equivalence, and for all dimensions and all ideals satisfy this.
I think it's a good guess. I don't know. Probably. Probably it's a characterization of H formulas. Should I repeat? If you also quantify all families, it's not equivalent to. Well, yes. The answer is yes. It follows from that.
It follows. It's the common theory of all structures.
Well, yeah, it's not much, right? Well, it's. Okay, so now I can characterize when the support function of the product is defined. And this is syntactic characterization. And maybe. Improve this here to cover. So, Farah. The following are equivalent. The family of MI recognize coordinates. I didn't say what it means. Two. And you can take two as a definition of the first if you don't know the first. I mean, the term is not empty, don't worry. It's going to be a third. Every reduced product MI interprets PI and the support function. Do you want me to recall what is the support function? The set of support function of support of AB is simply the set of I of indices such that AI equal BI and its modulo I. So it takes two variables and gives you a set of indices. And three say the following: x equals z, implying y equals z. If x equal to z and y equal to z, is an H formula. Is equivalent to an H formula in the common theory of all MI.
Sorry, so H formulas are not closed in their.
What's make this thing not an H formula already? It's not an H formula. If you try to put, you need quantifiers, remember. You need a for all quantifier. If you try to put a domain variable, it's not going to work. So, but for a very precise.
Yeah, and you're not formally closed in their.
So if you write this thing, exists omega such that x equals z, okay. And for all omega x equals z, imply y equals z. I mean, the first time I wrote this definition, I had to check that this thing is not equivalent to that. And this is an H formula, but it's nothing. Like here, if I say that there exists omega such that x equals z already, so I have no shot. So, no, it's not the same.
So the definition of recognized coordinates, this is depending on your choice of ideal. Or at least the two is depending.
No, it's for all ideals, sorry.
So two states for all ideal. Okay, yeah, that makes sense.
Thanks. I don't give a definition of one, I find it confusing, but it's a definition about automorphism. The equivalence between 2 and 1 is one of the instances where you can use the Berg definability theorem to convert a model theoretical statement into something about automorphism, which is not in nature, model theory in nature. So it's quite practical. So I guess example of application better, and I apply it immediately to groups.
So an example would be, so if I take the countable product of the rules,
Yes.
then the idempotent would code for the atomos, for the atomic Boolean algebra.
Yes.
On the
So you are citing the McIntyre direction. They do, okay. What they do is if you have what they call, if in your ring you have only two idempotents, 0 and 1, then you recognize coordinates. Then you can interpret the support function.
So recognizing coordinates, is it somehow the structure can tell apart those coordinates that we should be able to tell apart?
Yes. It means you are, I mean, the model theoretical statements say that the structure is well aware that it is a product. The first statement says that every automorphism of a product is what you expect, is a shuffling of the coordinates and maybe automorphism of the structures. But it's other than to state than what I said. I mean, I said what I meant. It was a notion of Ilijas Farah. He very well studied it. He had a few papers on it. Few other people has also discussed recognizing coordinates, notably. So I think there will be more better on that. Example now, remember? All right. I'm going to write 3' first. X equal E imply Y equal E if all MIs are groups. Okay. So if you are talking about groups, you don't need the Z, you just need X equal E imply Y equal E. Okay. Standard. Corollary. Let's assume for all I, MI is a group with the following property. For all A not equal to E, the centralizer, the set of elements commuting with the set I'm going to write, and here I'm writing the conjugacy class of A. Let me call it G. Is equal to E. This is a conjugacy class, a set of conjugate of A inside the group G. And every element which commutes with everything, well, is only E. If A is not equal to E. If A is equal to E, then you have everything here. You have G. So G is equal to commutator of EG. Sorry for trivialities. Okay. Simple groups, for example, this property S4 or Sn for n bigger than 4. So, example S4 Sn n bigger than 4 and simple groups. Maybe much more. Then I recognize coordinates. In all the sets I wrote above. Okay. So meaning, if I consider my product of S3, when this product is interprets this support. I'm waiting for you, Blas, maybe to complain.
Yes.
N equal 4.
Trying to see where I should
sorry. So we do it by n for n equals 3. But it's just worrying that it doesn't work for 3, but it's not a problem. Okay. I wanted to give another example with perfect groups. So I'm just stating it quickly, but I think I have to go on. Not spend too much time. But what we aim at the beginning when we worked on it is to characterize all groups which recognize coordinate. For example, could it be all the groups which are not product of groups, direct product of groups, and which has a non-trivial center? Trivial center, well, it doesn't work. Okay, so I give another class which recognizes coordinates, but which has a non-trivial center. And it was not obvious to get at the first place such an example. Non-trivial center, which is not a direct product. Maybe I should start with non-example first. Non-example. If G is equal to H times K, then G don't recognize coordinates.
Who are H and K?
Non-trivial groups.
Non-trivial groups.
Because one, if you take two products of G, then you can mix the H component of the first with the second component of the second. You can switch partially the coordinates and it's not fitting the definition. So it's something very easy to show. If, I think you will prefer the second example. If G is abelian, then G doesn't recognize coordinates. The product
so
of
G, you mean like an omega family of
G.
so
You cannot interpret the support in a product of G, in product
yes.
of Z, for example. Why so? It's because the product is itself an abelian group. An abelian group is stable. Stable structure don't interpret the Boolean algebra. Okay. Boolean algebra, which is of course nothing, not stable, not NLP. So that doesn't work. And the obstruction that we thought at the beginning is similar. So there is no more homomorphism from the group to the center. But it's not enough. So, okay. Maybe I can write down quickly my example here with perfect groups. Position. If assume G is quasi-simple, meaning G is perfect, is the commutator of G. G mod Z, the center of G, is simple. And assume that the commutator width of G is finite. every element is a sum of commutator, product of commutator, and here you ask for bound. Commutator width is finite. Then G recognizes coordinates. So,
Sorry, isn't every element a commutator by the G equals?
G is equal to the commutator of G,
Yes.
which means every element is a product of commutators, arbitrary product of commutators,
Product, yeah.
and a commutator with bounded, finite. I realized what I forgot to do also is to explicit the formula. So using this condition here, you can really well explicit how to define the support. I forgot to do it. Here, it's much less trivial, and it's depending on the finiteness. And it's really it's an example where it shows that groups don't recognize coordinates for the same reason. They can be for an integer m, and m is arbitrarily large. So with this examples of quasi-simple, SLN of f for n bigger than 2 and f of cardinality at least 4 is quasi-simple. It's not me, so and it's of commutator with 2 SLN of f. It's an old theorem, and I think there's some works about commutator with 1 for this course. So I am, how much time do I have?
Like 10-ish minutes.
So I can talk about the second part of the story, because here we haven't finished the story. We don't know what is definable on product of S3. But we know something.
Before you raise this, may I ask, so when you say you're 3 prime in the theorem,
Yes.
is it for pure groups or is it just for any language extending the,
Yes, it's a very good question. Okay. So, interpreting the support, you recognize coordinates. If you have more structure, you have more opportunity to interpret it. You have more definable sets. So it is, when I say group, it's enriched group, doesn't matter. If a structure recognizes coordinates, then any enrichment recognizes coordinates. It's upward close. The name of the paper is Coordinates Recognition, Groups and Other Surprises. We are 3 co-authors. We accepted the title of this paper, but we never discussed what it means, other surprises. So for me, surprised about this story, but I don't know if my co-author agree, is that the structure doesn't need much to recognize coordinates. Linear orders recognize coordinates. So for mini structure, cyclic group of 3 elements, cyclic order set of 3 elements recognize coordinates. So you don't need much. But for groups, the dividing line, which group recognize coordinates, groups which recognize coordinates don't recognize. It's really relevant, and we don't know how to characterize it. Pure groups. For all fields recognize coordinates. Because of what Leo said. Can you erase now? So, we have 10 more minutes, or maybe 8, to discuss what is definable in the product of Sn. And we know that Sn now recognizes coordinates, meaning that in the product of Sn you can interpret support function. But what about the support phi? Set of indices such as formula phi or it is also interpretable. And for that we also need H formula. So let's have a proposition. Assume that the reduced product I of mi interprets 6, but it's okay. Sup equality, the support function, which there is a set of indices such that A equal B, A equal BI. Then let phi be an H formula. Then sup phi to A associate a set of indices I such that phi of I holds is definable. The product and R with the structure L and give a formula sup. Or you also need for energy. You understand? So once you have integrated the support function in the language, sup phi is just definable, and it's just a trick. It's not a difficult trick. Which directly means that but if you want sup phi to be definable in your language, you just have to check that every formula is a Boolean combination of H formula. So the question now we are reduced to, sorry to go fast, but is every formula in S, N, and bigger than 3 a Boolean combination of H formula? If yes, then in the language of group, product of S3 interprets the language of Feferman-Vaught, and by Feferman-Vaught it eliminates quantifiers relative to Boolean algebra. And so we are done.
Sorry, when you say in Sn, do you mean every formula modulo the theory of an infinite product of Sn?
No. I mean, yes, maybe. I mean, you can also do that, but yeah, in Sn.
In one Sn or
In one Sn. Yes, you don't use parameter.
N is fixed, right?
N is fixed.
You fix N.
Ah yeah, in is fixed.
How many mi
Fixed N. Yes.
Omega copy of Sn.
Yes. Yes. Well, sorry, so I should have not put it as a question. The answer is yes. And yeah, sorry. But let me say something. Every type in Sn and fix is isolated. So when I say type, it's no parameter. When I say isolated, it's isolated by a formula with no parameter, by an H formula. And then you get that every definable set is a Boolean combination of H formula. It's a Boolean combination of types. And it's not obvious, this fact. It's much more obvious for S3, but not for Sn for every N. Yeah. So conclusion, I just write the conclusion and I stop. Product of S3, Sn interprets in language of group, interprets the language of Feferman-Vaught. And well, you can also take a subset of this language, and you are still going to eliminate quantifiers. You just need to take a formula isolated the types. That's all. Okay, so that's all I have to say. Thanks.